If A is any set, then there is no surjection of A onto the set P of A over subsets of. This is Cantor's theorem. George Cantor is assumed to be the father of set theory. There are many theorems in his name. This is one of the theorems. Now let us give an illustration on this theorem. You consider a set A having three elements x, y, z. And we have to claim that there cannot be a surjection of A onto P of A, the power set of A, which contains 2 raised to 3 elements, since there are 3 elements in A, such as A itself, empty set, singleton sets like set x, set y, set z, and sets having 2 elements like set xy, set yz, set xz. Now, if at all we can define a function f from A to P of A, since there are only 3 elements, maximum 3 images can be there. For example, x is mapped to set x, y is mapped to set y, z is mapped to set z, like that. In this mapping, you can see that there are elements or subsets of A like set xy, set yz, set xz, etc., which do not have any pre-image in A. That means this F cannot be a surjection. Now we are going to give an analytic proof for this theorem. Suppose there exists a surjection F from A to P of A. That means there exists a onto map from A to P of A. The P of A is a set of all subsets of A. If you take any B subset of A, that B is an element of P of A. Since F is a surjection from A to P of A, for this B in PA, there is an element B in A such that this F of B is equal to that B. Now this B, there is inverse image of this capital B, is an element of A, and the capital B is a subset of A. Therefore, there are two possibilities. Either B is an element of B or B is outside B. Now you take any element A in A. Then the image of A under F is an element of P of A. That means it is a subset of A. So for any A in A, F of A is a subset of A. Then there are two possibilities. Either A is in an element of F of A or A is not an element of F of A. Now consider the set of all elements A in A such that A is not in F of A, and let it be D. Then clearly this D is a subset of A. There are two cases as shown in the figures. This D may be like this or may be like this. Now, since there is a surjection from A onto P of A and D is a subset of A, D is an element of P of A. So correspondingly, there is an A naught in A such that F of A naught equal to that D. Since F is a surjection from A onto P of A, there is an element A naught in A such that F of A naught is equal to that D. Then either this A naught is in D or A naught is not in D. The first figure shows that A naught is in D. The second figure shows that A naught is not in D. So there are two cases. You take the case 1. That is A naught is in D. If A naught is in D, then by the definition of D, A naught is not an element of F of A naught, because D consists of those A in A such that A is not in F of A. So if A naught is not in D, is in D, then A naught is not in F of A naught. but f of a naught is d. That means a naught is not in d. So we are getting the condition that a naught is in d implies a naught is not in d, which is a contradiction. Now let us take the case 2. Case 2, the second figure, where a naught is not in d. A naught is not an element of d means, by the definition of d again, a naught is an element of f of a naught. A naught is an element of f of a naught. That is, a naught is an element of d because f of a naught is d. So in the second case, we are getting that if a naught is not in d, a naught is an element of d. Again, a contradiction. So these two contradictions fulfill the condition that there cannot be a surjection of A onto the set P of A or subsets of A. That is the Cantor's theorem. There cannot be a surjection of a set onto its power set.